Hello, my name is Alia and this is take 3 of the video. We're just going to go straight into it. I keep going over on time. So Real-Time Upscaling Analyzer, that's the app I made. It's based on the Microsoft DirectX graphic samples, and it's got a significant amount to change, literally an infinite amount of changes, based on GitHub's own information themselves. The main app is located in Mini Engine. Mini Engine consists of core and model, and these are where a lot of modifications live. So my wholly new additions are under the AZB folder, and then there's also like tweaks within the files that are done through comments. I've also added shaders. If we go into the app, RTUA, the solution, that's where the main entry point is for the project. You can see that RTUA is kind of main CPP. This is an entry point. I'll get it building. I tried to add a description of what every file did and how I modified it. Oh, let me just go back to it real quick. I added a change log depicting the changes I made, and then all changes in these files I prefix with this comment style to make sure that it's clear the work I did. And then in my own files, such as DLSS, I didn't do this because it was unnecessary. And then I have a utils file with like a global macro, so you can revert back to the original mini engine, and one for debug stuff, which helped me build the app for the experiment. Right, app. Right. This is the application. This is how it looks. Is it on OBS yet? There you go. You can use arrow keys to navigate the GUI. You can also use a gamepad. Enter in spacebar to interact with elements. We start the tutorial. Show them it's WASD to move, mouse for camera, left shift to change movement speed. I built all of this, by the way. The style and the highlighting of text. This is all custom built by me using the IamGUI third-party library, which is added as a submodule in Git. Left control M toggles between mouse input and the GUI. This is important for me to implement. Quite a lot of modifications. Because now you can kind of freeze the camera and interact with the GUI on the side. And then there's some guidance for participants and users about what scaling factor is, how to compare upscaling. And then I inform users about tooltips. And yeah, these are all the tooltips in the app. You can see this is the main window of the app. Sorry, I'm rushing a bit because it's hard. So let's get through. Display resolution. This is the resolution of your current monitor. Native resolution. This is the size of the internal rendering buffers. And then the scale factor, which is the heights of these divided by each other. So you can see currently the scale factor is 1 because we are rendering native. There's no scaling occurring. Yeah, these tooltips will explain all that, and you can restart the tutorial if you forgot the inputs or if you want to just look at the guidance again. But then there was guidance provided in the experiment too via a sheet. Okay, so what do we have? The main thing is you can change rendering mode. So you'll see now as we change to bilinear, the quality significantly changes, and this is because we have a scaling factor of 0.3. We are actually rendering at 480p and stretching the image to 1440p. Which is why it looks significantly worse than native. So then participants were instructed to kind of find equivalents between DLSS and bilinear first, which are the two upscaling methods. They begin here, and overall the final kind of goal of this experiment was to compare the distinguishability between native resolution and DLSS. And the first part of the experiment was kind of like training users up to kind of spot things more. So they were asked to see things in native. They're asked to kind of compare bilinear to DLSS. And the way you do that is DLSS, if we go into that, this was the kind of the main mechanic of the entire application and experiment. It has 5 basic modes. These are modes given by the NVIDIA documentation. So you have performance, balance, quality, and ultra performance. These essentially map to scaling factors. So ultra performance being the most heavily scaled and quality being less scaled. The idea that ultra performance is the easiest to run. You would then find equivalent scale factors. This gets remembered. So this is 0.33 480p. If we go to bilinear, you would then go and find a 480p resolution there. So now they have the exact same inputs. They're doing the same amount of scaling, and you would compare the quality. And I didn't say this to participants in the experiment, but DLSS clearly far exceeds that of bilinear, despite having the same amount of input information. So yeah, DLSS's reconstruction algorithm is really impressive, driven by machine learning, and that's the main crux of the app, was averaging things across these different scale factors between these two. So the 3 components were kind of static visual clarity, motion stability, which is why there's 2 different types of movement speed, and also why these particle effects are here. Now, these might look buggy. They're actually not. This is a limitation with Mini Engine. It's known. They are not properly time-stepped, and they're designed for 60 and 30 hertz displays. If you see at the top, my display is 240 hertz, or 240 FPS is what we're currently rendering at. This is with VSync on, which is why they look exceedingly fast. At university, where the experiment was run, and on your home computers, you'll likely have a 60 hertz display, and these will run just fine. It only looks weird on my fancy monitor. But the important thing still applies, where DLSS does have some weaknesses, so you might not be able to tell just yet, but there's a bunch of ghosting and smearing. If you were to go back to native, you can see these particles have a ton more clarity. And yeah, there's like an intentional ghosting because that's part of the effect, but you can see the difference in the other particle effects too, which are here. So say the fire, for example, when you are at a really lower kind of input resolution, you can see this kind of visible grid, pixel grid on the side, which is why these particle effects are included. Yeah, and then the final thing was to then compare to native. So if you were to have quality mode on DLSS, what is the detail retention like? Is it even distinguishable? And that was the crux of the experiment, the paper, and this application. Additionally, I just want to talk about a really hard piece of work I did because it was really, really hard. LOD bias, this is important for the DLSS algorithm, and this is part of what makes my implementation valid, and it meets the NVIDIA docs, where without the LOD bias has like a formula given in the documentation to be calculated, and it averages out to 1.7 at balance. You can override this and see the differences for yourself. And immediately when setting it to 0, if you look at the curtains here, you can see that a bunch of detail is lost. If you were to set it to a positive LOD bias, you can see that a lot of detail is lost. I mean, just look at these surfaces here and here, completely gone. Yeah, everything gets kind of blurry and smoothed. This is also the same in native, but you can see the effects aren't as extreme. With the same LOD bias of 1.0, it's not as extreme because DLSS requires heavily that the textures are sampled with the correct LOD bias. I mean, look at the detailing in the curtains now, completely gone at this point. All that darkness and all that crisp edges are gone. Oh, you can also enable and disable post effects, which is what I did. I did a ton of work for this project and I'm really proud of it. I keep going over on my time. I think this is as good as it's going to be. Thank you.